In this recording, we will discuss the work needed to assemble two charges, two unknown charges Q1 and Q2, a distance d apart. Now, the idea is to find the work needed to bring charge 1 here, charge Q1 to this location 1, then the work needed to bring charge Q2 to location 2, find the total work needed to bring them both, then finding the work done by the electrical force, and find the change in the electrical potential energy of the charges of the system made up of the two charges. Okay, what it boils down to, we have charge Q1 very far away, and we are going to move it to this position 1. Now, what I need you to think about is try to relate this to gravity. For example, if I have here a table and I have a block on top of the table, and I'm going to move the block from here to here. If we don't have any friction, the minute I get the block moving, I don't need to apply any force in the forward direction to get it moving. So the applied force is going to be equal to 0. That's if I don't need to accelerate the block. If I don't need it to speed up, to accelerate, the minute we get it moving, and you need an infinitesimal force, a tiny force to get it moving, the minute you get it moving, it's going to be moving without the need of any additional force acting on it. The forces need to be balanced for it not to speed up. So if my applied force is 0 when I'm moving it from here to here, then the work done by me, when I'm going to move it from here to here, is going to be equal to 0. We have a similar case here. Charge Q1 is very far away, and we don't have any charges in the neighborhood, which means I don't need to apply a force larger than 0 to move Q1 from very far away to position 1, which means that the work needed to move Q1 to position 1 is just 0. Okay. Now, the story is different for charge 2, because now we already have charge Q1 at position 1. To move charge Q2 from very far away to position 2, I'm going to need to do some work that's non-zero. Remember, the work to move charge Q1 was 0, but this one is not going to be 0. What is it going to be equal to? Recall what we had here. The work needed to move a charge Q1 from infinity to a position RF away from another charge is given, the work done by the electrical force is given by minus k Q1 Q2 over RF. So in our case, I'm going to rewrite the equation here. It says the work is minus k Q1 Q2 over RF. This is the work done by the electrical force. Since the force that I need to apply to move it has to balance the electrical force, the work done by me is going to be K Q1 Q2 over RF. In this particular case, RF is the final separation between the charges. Remember the equation again. RF is the final separation. As the monkey brings the charge. That's your RF. Okay. Which means in this case, the work done by FA is just K, Q1, Q2, and my RF, which is D. Now the total work done by me is going to be 0 plus the work done by the work done by me is going to be the work done to bring in charge Q1, then the work done to bring in charge Q2. So that's going to be 0 plus K Q1 Q2 over D. The work done by the electrical force, since the electrical force balances the forces that I exert, so it's going to be the opposite of the work that I exert, so it's going to be minus K Q1 Q2 over D squared. Over D, sorry. Now, the change in electrical potential energy is minus the work done by the electrical force, which is in this case K Q1 Q2 over D. Okay, now if these two charges were positive, you notice that the change in electrical potential energy is going to be positive. If they are both negative, the change in electrical potential energy is going to also be positive. Now, if they are of opposite sign, the story is different, and the change in electrical potential energy is going to be negative, because we are going to multiply a positive charge by a negative charge. Now, what if we would like to assemble three charges? Same idea. The work done, the work needed to bring the first charge is 0. The work needed to bring the second charge is the same thing as we found in the previous problem. It's going to be K Q1 Q2 over D. Now the question, what would be the work needed to bring the third charge? Now, in this case, we have to worry about two forces. Each of the charges, charge 1 and charge 2, are going to exert a force on charge 3. So there's going to be a work done by the force due to charge 1 and a work done by the force due to charge 2. In other words, it's going to be W1 on 3 plus W2 on 3. I need to overcome two forces here. Now the first work is going to be, the expression for the force is the same, K Q1 Q2 over R squared. That's the expression for the force. So in this case, it's going to be K Q1 Q3 over D, and then for W23 it's going to be K Q2 Q3 over D. Remember here, the key here is when I'm doing the work, I have to overcome the force that these two charges exert on each other. And what's that force? That force of 1 on 3 is going to be K Q1 Q3 over R squared. And I also have to overcome the force exerted by charge 2. And that force, F2 on 3, is K Q2 Q3 over R squared. Okay. Now, my overall work, the total work, is going to be just W1 plus W2 plus W3. I'm running out of space, so I'm going to write it here. In this case, that's going to be 0 plus KQ1 Q2 over D. Remember here it's an easy where all distances are the same, plus KQ1 Q1 Q3 over D plus K Q2 Q3 over D. That's the total work. The work done by the electrical force, since the electrical force is opposite to the force I apply, is going to be just minus the total work. And the change in electrical potential energy is the negative of the work done by the electrical force, which is the negative of the total work, or just the total work exerted by me. That's the change in electrical potential energy. Okay, let's look at some other examples. Okay, here it is asking us how much work would it take you to assemble 3 negative charges. Okay, to assemble 3 negative charges. Okay, we'll go back to what we just found out. This is the work that it would take you to assemble any charge. Now look at the first term. Q1, Q2. Positive, negative times negative. That's positive. Negative times negative. That's positive. Negative times negative. That's positive. So all terms are positive. Okay? Which means my work is going to end up being positive. Okay? Remember the equation that I wrote? Anyway, I'll rewrite it again. Work total is going to be K over D. I'm going to factor it out since it's the same. Q1, Q2 plus Q1, Q3 plus Q2, Q3. Since all of our charges are negative, each of these terms is positive. That's going to make the overall work is positive. Okay, now here, what about in this case when we have a positive, negative, and a positive charge? The total work required to assemble the set of charges is going to be what? Okay, I'm going to rewrite the expression that we just wrote. The work is K over D, and said it's Q1, Q2, plus Q1, Q3 plus Q2, Q3. Okay, this term here is positive. Q1, Q3 is negative. Q2, Q3 is negative. Now, they don't precisely say it here, but if to assemble the set of identical charges, now if the charges are identical, I have 2 negative terms and 1 positive term. That means my work overall is going to be negative.